Normal distribution is for one data set, one variable only. If we've got two variables, two data sets that we want to see if there's some connection between them, such as the height and the weight of people, are they related? You would expect they might be, but you could do a study to find out. That's when we can use correlation. But there's one important rider here. At least one of the data sets or one of the variables has to be a continuous one. It has to be measured as well. If you've got two counts, we have to do the chi-squared, which we'll come to next. But if at least one of the data sets is continuous, then you can do correlation analysis. And here's an example of one here. There's generally 4 basic steps you go through if you're going to do correlation. The first one, draw a scatter plot of the dependent variable versus the independent. And if you can't really tell which might be the dependent and which might be the independent, then it doesn't matter, just plot them in any order. But generally, if it makes sense to have a dependent and an independent, the independent variable goes along the x-axis. As in the graph here, they're looking at the life expectancy against the number of packets of cigarettes you smoke a day. So the independent variable is the number of packets of cigarettes, goes along the x-axis, and the dependent variable you're testing for is your life expectancy. Okay, so first of all you draw your scatter plot and you see if you just visually can see if there seems to be some connection between them. Is there some pattern to the dots? And certainly in this case it looks as if it might be a little bit fudged, I'm not sure, but anyway, the dots are going down in quite a straight line there. And then the next thing is to draw in the line of best fit. Now we can do this 2 ways. We can just do it ourselves visually, in which case we just call it. We say we've by eye we've put in the line of best fit. You can get the computer or your calculator to do it, and it's then given a flasher name. It's called the regression line, because the computer or the calculator will use regression analysis, which we don't need to worry about here, but they will use regression analysis to get this line of best fit. And so that's called regression. It's just a way of finding the line of best fit, which you can do by eye, but the computer maybe does it better. And then you've fitted a regression line. The strength of doing the regression analysis is that the computer will also come up with an equation for the line if you need that. So draw the scatter plot either by eye or by regression, getting the calculator or computer to do it, put the line of best fit in, and also we'll then find a regression coefficient for you, or we can just call it a correlation coefficient. And that's very useful to have. It's a number. And if we're doing math studies, it's nice to have a number. Makes us feel more secure or something, I don't know. Anyway, it's nice if you've got a correlation coefficient you can put in your results. And we'll see what that means soon. And then finally, you draw some conclusions. And this is where you can go terribly, terribly wrong. Be very, very careful what conclusions you state on the basis of correlation analysis. I'll come back to that soon. GeoGebra is great for doing scatter plots and the regression analysis, getting the line of best fit and the correlation coefficient. If you're going to be doing this in your project, I would suggest using GeoGebra because it gives a nice plot that you can easily export into your write-up. If you're not going to be doing this in your project, then maybe you don't need to bother with GeoGebra, although it's very easy. I can quickly show you how to do it. But you do at least have to learn how to use your calculators to do correlation coefficients, because you've got to be able to do that in the exam. Anyway, here we go with GeoGebra, just to show you what correlation is about and what the correlation coefficient really means. So I read an interesting article just the other day. Apparently our happiness is related to the activity level in our lives, however you measure that. But if we're very active, we're more likely to be happy. Okay, that's nice. So I've just made some fake data up. This is not their results, I'm just showing you. I've no idea if this is sort of the level of correlation or not, doesn't matter. What I want you to look at is keep an eye on this number here, because that's the correlation coefficient. GeoGebra gives us that, and if I change any of the data, it will change that correlation coefficient, the B. So I'm going to be changing the data soon, and I want you to see how that B value changes. First of all, let me get GeoGebra to put in the line of best fit. Look at that. Very nice. Would have you put it there? Maybe, probably somewhere there, but there is a big difference from how the calculator or computer does it compared with how students want to. And I want to stress this because students often think that the line of best fit is the one that goes through the most points somehow. That's not right. It doesn't have to go through any of the points. The line of best fit is the one that sort of overall, on average, they are closest to. And that's what the computer has done. It's just many times found the difference between the points and the line it guesses and made that a minimum. Doesn't matter how they do it. But that's the point. It does not have to go through any of the points. And if you do a line of best fit just by eye, don't force yourself to put it through points. Just sort of try and get it overall closest to most to them. Okay, so that's the line of best fit that GeoGebra will quickly do for us. Now, here we go. So you're watching B over here while I change some of the points. What I'm going to do is bring them closer to this line. Okay, so A is a little bit far away. Let's bring it in. And so I'm going to bring A down a little bit. You watch what happens to the correlation coefficient. Bring B in. The line's moving a little bit, of course, because the points are changing. But I want to know what's happening to that B, that correlation coefficient up the top left there. It's now up to 0.84. Bring G down closer to the line, 0.89, up we go. Okay, well I think you can see the pattern here. In fact, if the points are perfectly on a straight line, then the correlation coefficient, this B as GeoGebra calls it, would be 1. Now I want to play around with these points a little bit more and show you what happens. So I'm going to take A up there, bring F down here. Now what's happened to the correlation coefficient? It's gone negative. Does that make sense? You think about your geometry days, what you know from geometry. What's the slope of this line now? It's negative. So the correlation coefficient, the sign of it, positive or negative, is related directly to the slope of the line of best fit. If it's positive, one variable is going up as the other variable goes up. So happiness goes up as activity level goes up. If the correlation coefficient is negative, the slope of the line of best fit is negative, and that would mean that one variable is going down as the other goes up. So if this were our data, then we would be saying that happiness actually drops as activity level increases. That wasn't the finding at all, but I'm just showing you what the meaning of the correlation coefficient is. So what's this getting closer and closer to? As the lines get closer and closer, as the points get closer and closer to a straight line, but sloping down, then the correlation coefficient gets closer to -1. So either -1 or +1 is a perfect correlation, either going up or going down. And the closer to 0 it is the weaker correlation. Let me see if I can get something approximately 0. What would I have to do? If the correlation coefficient is 0, look at the gradient of the line. Let's go back to the graph I showed you earlier on about happiness and activity level with my fake data. But suppose it did look something like this. We did the regression analysis, got the correlation coefficient of 0.72 there, which is moderate. And we would write up our conclusion saying, we have evidence that increasing your activity level increases your happiness. Wrong. This is the mistake that many, many people make. Students, teachers, researchers, the media, the public, and so it goes on. The mistake is assuming that correlation means causation. That just because there's a connection between the variables, we often jump to the conclusion that one is causing the other. But our results here don't show that activity level causes happiness. So saying that becoming more active in our lives is going to make us happier on the basis of this data alone, there's no evidence for that. It just says that if somebody is more active, according to these data, they will be happier. But it's not saying that the way to become happy is to become more active. That's a subtle point. Let me make it clearer with some ridiculous examples. And then I want you to think about more subtle ones like this that get presented to us almost every day. And we tend to buy it. But I want you to become much more critical in reading so-called scientific reports or research shows and all this nonsense that we get thrown at us. Right, here's some nonsense stuff. I want you to then start thinking about more subtle ones. Okay, there are all sorts of cures for headaches, aren't there? And waking up with headaches, no fun. Well, here's a study that shows us how to stop that. Sleeping with your shoes on is strongly correlated with waking up with a headache. So, it's very simple, according to the study, you see. If you don't want to wake up with a headache, then don't sleep with your shoes on. Convinced? All right, here's another one. Ice cream sales have a strong correlation with the number of drowning deaths in a day or a month or whatever, however we measure it. But no one is suggesting that banning ice cream is going to reduce the number of drownings. I mean, that's just nonsense. And yet this is the sort of thing we are getting fed, the same sort of reasoning. Here's another one. Carbon dioxide seems to be public enemy number one at the moment, so let's see if we can add to its list of crimes. Well, since 1950s, both the atmospheric carbon dioxide level and obesity levels in the United States have increased sharply. So, it's obvious. Carbon dioxide causes obesity. Or, what about this for a side effect of carbon dioxide? Since the 1950s, both atmospheric CO2 level and participation of women in the workforce have increased sharply. There is a strong correlation between those two. So, our conclusion? Carbon dioxide makes women want to work more. Well, okay, that's enough. Often two variables can seem to be related, can have a strong correlation, but it doesn't mean that one is causing the other at all. It might be, I'm not saying it isn't, but we can't assume that just from a simple correlation analysis. And too often that's all that's done. Two variables can be strongly correlated mathematically, but have no relationship, no causal connection whatsoever. They might just be going up together by chance, that can happen, or often there's a third variable that's driving both of them. And if we don't understand that third variable, then we are missing out on the true causal connection. So you will often see examples of drawing false conclusions about causality based on simple correlation analysis in medical experiments, food and nutrition studies, environmental studies, biological studies, behavioral studies, and so it goes on.